to get started. So we are now looking at our next chapter. Well, in a lot of ways, it's kind of regurgitating old stuff. I'm going to have to close this now, shooting space. Let's try this again. Okay, everyone, we're going to be starting this chapter here. I believe it's chapter, darn it, I forgot the number. I think it's chapter 14. We're going to look at confidence intervals for single means. And then after that, later on in the week, we're going to be doing confidence intervals for two means, the difference between two means. And it does share a lot, but not everything, with population, estimating population parameters, where it's proportions. The main difference is that we're going to be using magic t-scores. These change, and they change depending on the confidence interval that you want, like a 90 or a 95 or a 99, but they also change according to n, which is the sample size. And I have a table, which we've used before, which essentially gives you the magic t-score that you would use in calculating a confidence interval. So let's give you the generic version of what the formula looks like. If I wanted to say get a 95% confidence interval of a sample mean, right? It'd be X bar, the sample mean, plus or minus the magic t-score for 95% times the standard error of X bar. And the formula for the standard error is just the standard deviation of the sample divided by the square root of n. So this formula would look something like this now. Not really too bad, right? This takes the place, right? The standard error for means is not p hat q hat over n, right? That's what it would be, you know, if we were doing proportions, right? The square root p hat q hat over n is this guy, right? But you can live with that, right? Not that bad. This is the fella that's going to cause you the trouble. In proportion, it didn't matter how big the sample size is, right? It didn't matter how big that n was, as long as it was big enough to be usable. Wasn't it always the same number? Does anybody remember what the magic z-score for 0.95 is?
1.96.
Sorry. And it's 1.96, whether there's 10,000 numbers in your sample or 4,000 numbers or 82. But this guy changes. And he changes depending on the size of n. And just to add a little hiccup to the problem, we don't even use directly n. We use a guy called degrees of freedom, which is actually n take away 1. So you could say that the size of this depends on the value of n minus 1. And we have a table that we go looking up that tells us who this number is, or at least approximately who he is, because they have to round things off. And that's when this fella here comes into play. Now, I've got this on canvas already. I've got two windows open right now. Can you see the window with your faces, and can you see the window with participants, or do you only see the table? What are you seeing?
Only table.
Oh, thank goodness for that. That means I don't actually need to move all my windows over to the other side now, so that you don't get distracted. Right. Okay, so let's show you how this table works. Suppose there was 20 people in my sample, right? I'd go down to row 19, because 20 people means degrees of freedom of 19. Okay. So far, so good. Now, who do I want to be my magic T? Well, it depends on what confidence interval I wanted. If I wanted a 95% confidence interval, do you see that the answer is 2.09? So that would be the magic T-score, right? The 2.09. Suppose I had, make it nice and easy, 51 numbers in my data, right? Then degrees of freedom would turn into 50, and it would be here. And can you see that my magic T-score has now changed to 2.01? If you read down the column, can you see how the magic T-score changes? For most of its life, isn't it 2 point something? But it's still decreasing. Once you get to around about the bigger numbers, right, like sizes of 100, for instance, it's 1.98. And if you get to about 1,000, right, so you've got 1,000 people in your sample, do you see that the magic Z number is pretty darn close to the guy they're calling infinite? And do you recognize infinite as the Z score? So what that says is that the student T distribution, that's what the magic T number is, takes different values depending on the sample size. But as the sample size gets bigger and bigger and bigger, let's say for practical purposes, up to about 1,000, by the time the sample size gets to 1,000 or beyond, right? So 4,000 people, 20,000 people, doesn't your magic T score just turn into your Z score? Right. That's how that would work. So if I would comfortable about how you find the right T score, right, the magic T score for an interval, depending on the size. Okay. So let's pretend that I wanted to get, oh, I don't know, can you actually read this? Can you read the numbers? So if I give a question, you can give me an answer. Right, suppose I wanted a 90% confidence interval and my sample size was 20. What would the number be?
$1.73.
Okay, let's say 90%, and it would be, you nailed it, 1.73. If I wanted a 99% confidence interval and I had 91 numbers, who would I use as my T-score?
$90.
What would be the T-score for 99% if I had
Oh.
91? So yeah, you're right, I would use row 90.
Right.
But what T-score would I use with that 90?
2.63.
Agreed, right. Are we getting a little bit comfortable? Because you're going to use this table a lot today and certainly tomorrow in your homework and so on. So I want you to be good at it. There's going to be some rounding off here. Have you noticed that this table goes to 2 decimal places? And so there is a possibility that WebAssign might ding you because it rounds off better than you did, because you can only do what the table's got you, and they've got fancy computers that do it to more decimals. I will try and make sure that I've put a tolerance on the answer so that you should get it by. But if you finally do 5 shots and you find out you're out by a 0.02 or something, tell me and we'll give you the points. What happens then when you have a sample size and therefore a degree of freedom that isn't in the table? Well, you can see it's really good up to what, 30, right? But what happens when you get 52 numbers in your data or 107, right? You got to compromise, right? Right, so if there was 120 numbers, let's just say 120 numbers, there isn't 119 in this table. Don't you just round off to the 100 mark and you choose, depending on the confidence interval, you choose one of these guys, right? So if you have a sample size that doesn't fit the table, basically take the one that's closest to it. If you want to be really safe, take the one that's below it. Right. So just round to 30, even if it's 37, you know, that would be safer. There's very little difference between the choices that you might have got, right? Very often they're either the same or 0.01 or 2 different. So that was kind of a preamble to what we're going to do. So we are going to estimate using this guy here. Oops. Confidence intervals of various types, and we're going to look at this type first, and then I'm going to talk about this kind of question later. So suppose you got some rabbits and you weighed them, and God, I don't know what a rabbit weighs. They weigh 3.5 pounds in your sample, and your sample had 52 in it. And you want to use this data to estimate what you think the typical average weight of a sample, weight of a rabbit is based on this sample. So I've got X bar, plus or minus, and we want a 95% confidence interval on it. So we're going to do that guy, right? This fella is 3.5, and of course you'll have to be told who S is. So it's 3.5 plus or minus a guy I haven't got yet. S over the square root of n. And that becomes 3.5, give or take a guy I still don't have, 0.4 over the square root of 52. And then I go and I look at that table, and the degrees of freedom should be 51. The closest number I can use is 50, so that's the one I'm going to do. And 0.95, 95 is here, and a 51. And if my eyesight is telling me the truth, it's 2.01 I'm going to use. Right, so you're comfortable about the formula that we're going to use and where each of these numbers either come from. Most of them you're just told, and one of them you have to look up in a table. And once you put that package together, we're going to get that the average weight of rabbits in this location is 2.01 times 0.4 divided by the square root of 52. And the answer to, let's say, 2 decimal places is that guy. This guy here is called the margin of error. What do you think would happen to the size of this number if I actually collected 500 rabbits in my sample instead of 51?
It would be smaller.
It would be smaller. This magic T would be smaller. This would be bigger, therefore that would be smaller. It would just be more accurate. Smaller margins of errors means that we have a more accurate kind of result. In this case, it could be as low, as light as 3.39. It could be as high as 3.61. So in this question, what we are saying essentially is that we are 95% confident that the true population average weight of rabbits is somewhere between 3.39 pounds and 3.61 pounds. So what kind of conclusions or evidence could that give me? Well, I could say that this is evidence that the average, I guess I should call it the mean weight of rabbits is more than 3 pounds. Would you agree? And how would I argue that. I'd say, look, I may not know what one of these numbers between here and here is the true average weight of rabbits, but I do know that all of these numbers are bigger than 3. So logically, I would assume that the average weight of a rabbit is more than 3 pounds. I could also do it from the other perspective. Isn't it also true to say that the average weight is less than 4 pounds? If I wanted to tweak it, couldn't I say more than 3.3 and less than 3.6 if I wanted to, crunch it down? But I'm picking nice big round numbers. Does that guarantee, this interval, does that guarantee that the true average weight of rabbits is in fact somewhere between here and here? Does it? Right, shake your head, no. Isn't there a 5% chance that the real answer is some totally different from this? Right, who knows, rabbits could weigh 8 pounds or 2 pounds, right? We don't know based on what has just happened here. So far, so good. Pretty standard question. So let's look at one more of these, and then I'll have a shot at showing you this fella. So let's see. Let's suppose we took a sample of 500 adults. And we measured, I'll make this up. We'll measure their cesium level in their blood. Why anybody would actually do that. And I don't even know if you get cesium in your blood, but they measured it. And it ended up being 4.1 units. And that the standard deviation was 0.3 units. And we would like to, from this sample, estimate what the average cesium level in an adult would be. Well, we've got our X bar, plus or minus. Oh, and we want to be 99% confidence interval, right? So X bar is this fella, and the standard deviation of that guy. This one is 4.1, plus or minus this guy, 0.3 over the square root of 500. And the magic t-score for 99%. 500 is pretty big. I'm going to be picking for a 99%er. Well, I can either pick 1,000 or I can pick 100. It's closer to 100. I'm going to pick it because it's 499, and that's only 400 away, so 2.63. And so it's 4.1, give or take this fella. So it's 2.63 times 0.3 divided by the square root of 500. And the answer we get is 0.035, 3 decimal places, which means that it's 4.065 all the way up to 4.135. So I'm 99% sure that the average cesium level in your blood is between these two numbers. They are very close to each other. And the reason I would assume that this has happened is that the sample size was a decent size. Now, you can use intervals in all sorts of ways. We could use them in the way that we just did earlier, that says, look, there's evidence that it's bigger than 3 or less than 4. So I could say there's evidence to say that cesium level should be bigger than 4, right? And what, less than 4.2? Agreed? But I could use it in a totally different way. Suppose you measured one patient and his cesium level, as a him, was 3.7. Wouldn't that be evidence that that guy's got a cesium level problem? He is distinctly different from what the average should be. Or a 4.5 would be distinctly high. So couldn't you use this range in a slightly different way? You could use this range to mean the normal range, right? Like 99% of people would probably have a number somewhere in that range. And anybody who's not has probably got some illness that affects your cesium level. I believe you can tell me that if I'm wrong, because there's probably some nursing people in here. Doesn't your thyroid gland have a lot of, one of its job is to produce or signal to the body to make various chemicals? Is that what your thyroid does? Is that one of its jobs? It tries to keep your hormones and various other things like that balanced. That's its job. I get a sort of a pseudo nod, so pretend I'm telling the truth. So you can look at this and you could say, you might have a thyroid problem, right? And that might be what the doctor would then go and look at. Oh, might as well share something, because you know what I'm like, I tell you all sorts of things. Quite a few years ago now, it was about 7, 8 years ago, I had a pituitary gland tumor. So it's basically a tumor in my brain. And no, it did not affect my personality. I was always this weird guy anyway. But it grows on your pituitary. You don't know about your pituitary gland. It's right in your forehead, and it's a little gland that's like this, and it dangles in your brain. And it produces various hormones, or at least it produces chemicals that signal your body to produce hormones. So if you have a pituitary gland tumor, you can have two kinds. You can have the one that I got, which didn't do anything to my hormones. It just grew bigger and was basically going to kill me until they discovered it. And the other kind you get, the tumor, it actually does what your pituitary gland does, but it does it like, it produces too much. So one of the side effects of some of the people who had it, for instance, if you know a guy called Andre the Giant probably had it, it signals your body to keep growing. It produces growth hormone. So even when you're an adult and you shouldn't be growing anymore, you do. It can also influence your testosterone level, which for males probably makes them rather aggressive, but for females, that's not good news, because females do have testosterone. So sometimes they can detect it by those symptoms. So when I was getting tested, the doctor asked me a really strange question. He says, has your feet got bigger? Because sometimes if you've only got a little bit of growth hormone, your feet get bigger, evident. Now, I had none of that. So I got in, and it's really cool what they do to you. And it'll put you off your dinner. They bore a hole through the bottom of your palate, and they bore another hole through your nose to get into your brain. And they stick these tubes up, and there's cameras on them and little grindy things with suctions, and they basically shred the thing to death and suck it through your nose. And if I had that same thing 30 years ago, I would have died, because the old way of doing it was literally to saw off the top of your head and pop the head out and get to it from above, because that was the only way they could get to the damn thing. Right. And the failure rate was so high. I mean, it was such a traumatic experience to your entire body having that done to you, that the death rate was astronomical. And a lot of doctors wouldn't even try it because it wasn't worth it. And now we got keyhole surgery. So I was born in the right place at the right time. And as far as I know, I get checkups all the time, and I have to take some medicine because you can't tell when the tumor stops and your real pituitary gland starts. So they basically destroy most of your pituitary gland to make sure they killed all the other thing. So I take some medication to cure that. But I wish they'd given me some growth hormone, because I figured out if I could grow to about 6'6", I wouldn't be fat anymore. No. You know, keep the same weight, 6'6", bingo. Wouldn't that work? David, you're smiling. I think that is logically, that makes sense, doesn't it? That I'm not overweight, I'm just the wrong height. Nakia, you back me up here? Right. Okay, let's continue then.
Sorry, I'm too busy laughing.
Okay, let's just continue. I want to show you this one, which is also going to be a confidence interval, but it's a standard deviation, what's called a paired difference. So what is a paired difference? Imagine, this would be a good example of this. Let's suppose you did a before and an after. And in the before, let's say it's a diet program, right? They've got this new pill you take and it's meant to help you with your diet, right? It helps you lose weight, right? And so you have a before and they weigh you, and they have an after thing when you weigh. And then what they do is they calculate the difference. And it's called a paired difference because for each person, right, there's a before weight and an after, and then the next person a before and after, and the next and the next, right? So you can see that the data started off as two numbers, right? A before or an after, right, for each person. But you just subtracted it, and it's the difference that you use. So can you imagine that the before and then the after, if you take before and subtract the after, shouldn't it hopefully be, if it's a working thing, that you lost 4 pounds, right? So there's a 4 pound difference. And this guy did really good, and this girl did really, really good. And this guy, he found a way of gaining weight by taking a diet pill. Weird things happen, right? Some people do all sorts of things, right? So this is the data that we use. And when you get its sample, its little X bar guy, it's very often got a little D next to it. And that just means it's the mean of the differences, right? And we would like to know a 95 or a 99 or whatever percentage confidence interval based on this data. And this data has a standard deviation, which we put a little D on it just to note that it's the standard deviation of the differences. And let's say that in this case, it was 7, positive 7, and the standard deviation was 3. And we conducted this with a sample size of 200 people, right? Pretty decent size. Let's find a 90% confidence interval from this experiment. The good news is that the formula doesn't look particularly different. And this standard error, I mean, basically, if you rubbed out the D's, isn't it the exact same formula that we've already been using? Isn't it just the mean standard deviation divided by square root of n? And 200, right, has a degrees of freedom of 199. And if you want to find the 90% one, my screen has disappeared on me here, so I'm going to have to open it up. Oh, come on, stop being a pain. There we go. Where is it? 90%, gotcha. Scroll down. 1.66. So it's 7, give or take 1.66, 3 over the square root of 200. And we have a 7. No, I don't need to type that in. I have a 1.66 times 3 divided by the square root of 200. And I get plus or minus 0.35. So 6.65 to 7.35. So if this new pill was if the experiment was done fairly, right, unbiased and random sample and all that good stuff, you could say that people using this pill to help them diet will use, well, somewhere on average, won't they lose between 6 and 7 pounds? That's cool, right? And you could say more than 6 and less than 8 if you wanted to do it that way. Can we pretend that we had a different diet pill and the answer ended up being that interval? I mean, because you can get negative numbers. In fact, if the answer was negative, wouldn't that be the opposite of a diet pill? Wouldn't it be a pill that made you gain weight? Which seems strange, but there are people who need to gain weight, don't there? So I can imagine there is such a pill, right? It improves your appetite or something. Very often these pills, you know, the diet pills, they fall into two, as far as I remember, two main categories. And one of them is they are meant to increase your metabolism rate. They have lots of caffeine in them or drugs like that, stimulants. They are downright dangerous things to take. If you're a healthy person, I'm sure you're fine. But one of the side effects is that they can make your heart race and they can overstimulate your body chemistry and do some bad things to you. So you could actually do more damage using a lot of these pills. So many of them are not prescribed by your doctor because they're just not worth it. And diet suppressant, the other technique that they use is diet suppressant, which is you take the pill and it just doesn't make you feel hungry. And so the idea behind that is you don't eat as much. But some people don't eat because they're hungry. Don't a lot of people eat as a psychological thing? It's not that they need the food. I mean, they're already full. They take it for comfort and other reasons. So if you're suppressing their diet, it probably won't do much good to them because they were going to eat even if they didn't feel hungry. So, but anyway, as I drift, we got it. That could harm. And if that happens, there is no evidence that that pill is actually, on average, going to improve the diet, right? It's not going to help you lose more weight. Wouldn't that be the equivalent of the p-value? Remember the proportion ones where some numbers are positive and negative, that if 0 is in the interval, it means there's no evidence that it's doing any good. You like that, Glenn? New kind of question, a new way of looking at data. I think I'll do one more of these guys. Totally made up, wish this was true. They had the before IQ and the after IQ. Now, evidently you don't know this, but drinking Guinness improves your IQ. It doesn't, but I'm pretending it does. And so they conducted an experiment and they gave someone an IQ test before they drank any Guinness, and their IQ, say, was 101 for the first person, and they took some Guinness and it was 103, and they done the before and the after and the before and the after, and they did it to 20 people. And they found out that the average of the differences was 5, and that the standard deviation of the differences was 1. We are now going to create a 90% confidence interval. Before I even calculate this confidence interval, let's rip it apart as a bad experiment. What's the first most glaring thing that's a problem with this experiment?
Sample size.
Yeah, that kills it stone dead. Do you know, if I get lucky or unlucky, whatever way my brain wants to go, couldn't you get 20 people who do actually get better with their IQ after a couple of drinks? I've been told by a few idiots in my life that they drive better after they've had a couple of drinks. They don't. They just think they drive better. because I've been in cars when they've done it, and they ain't any good. They're not that good when they're sober, but definitely not good. But alcohol gives you a false confidence. So maybe somebody says, I think after I've had a couple of pints, I'm more intelligent than I used to be. So I would just be really worried about the whole experiment. Let's see what the confidence interval tells us. It's this guy, plus or minus a magic t-score, and that guy. So it's 5 plus or minus. Right, I'm looking at 19 degrees of freedom on a 90%er is 1.73.
Professor,
Yes.
Melissa's in the waiting room.
Oh, thank you for telling me. She's now in. Standard deviation is 1, square root of 20. Let's find out what that looks like. 1.73 divided by 1. No, 1.73 times 1 divided by the square root of 20. And the answer we get is give or take 0.39. So you have, allegedly, according to this experiment, if you take Guinness, your IQ will improve somewhere around about 45 points. But we've already destroyed it with that guy up there. Can anybody remember what the size of a sample should be before you start feeling comfortable? It's kind of vague rule of thumb, but how big should a sample size be to feel that it's worth even doing the experiment, this stuff? I hope I mentioned it once. If not, I'm going to mention it now. About 30, right? Rule of thumb, right? We don't like samples smaller than 30. They are very, very susceptible to variation and false conclusions. Plus, there's a 1 in 10 chance that that's wrong anyway, which it probably is. Oh. Suppose I did a really big sample, and it was 1,000 people, and I got this answer. Everybody's negative. What's that evidence of?
It decreases their IQ score.
By somewhere in the region of about a point, right? And based on the fact that that's a really big sample size, shouldn't I be much more happier about the entire experiment? So although theoretically we are 90% sure the right answer is in here, we're making the assumption that it was okay to do the experiment in the first place. And if it's not okay to do the experiment, anything that you get from that point onwards is really fraught with danger, and you should avoid spending too much on that. Oh, by the way, side issue. Suppose Guinness decided to do a little 20-person experiment and they got this. Couldn't they put in their advertisement, drink Guinness? It helps to improve your intelligence. Technically speaking, if the advertisement company said, oh, wait a minute, you can't really do false advertising, they could say, look at 20 people, here's the statistics. It kind of works. Well, it doesn't really, but can you see that they've got some kind of pseudo background to it? Have you ever seen radio adverts or radio stories, more likely, that say things like, drinking wine, red wine, helps you live longer? You ever heard ones like that? I think they talk about the Mediterranean diet. Have you ever heard that then? That people in the Mediterranean typically seem to live longer than, say, Americans do. And they attribute that to things like red wine, right? Because they drink a lot of red wine in the Mediterranean, evidently. You've seen those things? Have you also seen things that says drinking alcohol is bad for you? So how do you put together the fact that drinking red wine helps you live longer, but drinking red wine also is bad for you? Well, the contradiction is based on the fact that they're using two different experiments, right?
But
They've looked
also
at
neither
people,
one says how much.
or how much. Yeah, drinking wine in a glass or two, I'm sure probably wouldn't do any damage to you and might well help you live longer. Drinking it in 3 or 4 bottles a day would probably not help you live longer. So quantity is an issue. I also believe that they don't take into account when they tell you things like that, lurking variables, right? Confounding variables. Mediterranean lifestyle is a very pretty lifestyle. If you've ever been to Mediterranean, it's a gorgeous place. And people are outside much more often. They walk around, enjoy the sunshine, they swim in the sea, they exercise a lot. They don't watch TV as much because their culture isn't as heavily, they don't have as many couch potatoes as we have, and all sorts of other things. You see that entire lifestyle is contributing to their life expectancy, right? All sorts of things, food and wine and weather and, oh, I love the Italian. Do you know this is stereotypical. Italian mindset was I've been in Italy a few times. The Italians are such happy people. They don't seem to stress out anywhere near as much as us. If it's not happening today, it'll happen tomorrow. Isn't that kind of the Spanish thing? Mañana, tomorrow. So if they have a much less stressful kind of life, I think that probably gets you a couple of extra years. So, side effects. To finish with, are we comfortable then that if you have a before and after set of data, that you can find confidence intervals just the same way that you do it for a single set of data? You can do it with paired differences, right? That's what these are. And are we comfortable about what the intervals tell us? How we can say this is statistically significant, that something is bigger or less than the other one? Or that if there's a 0 somewhere in the interval, that it tells us there's no evidence.